this example is a constraint optimization example applied to an economic problem, and it's what we call a two-period utility optimization problem. And let me explain what we mean with this. The function which we want to optimize or maximize here is this function. It's a utility function. You can think of yourself, for instance, or just an individual who wants to maximize utility over two periods, period 1, period 2. And what matters for the utility, and of course that's a super simplified model, is how much you consume in each period. And we call that consumption in period 1 C1 and consumption in period 2 C2. And the utility function is formulated in this way: C1 to the power of 0.5 plus 1 over 1 plus rho times C2 to the power of 0.5. Now this rho is a parameter of that utility function, which basically determines of how strongly you discount future periods consumption. The bigger that rho, the more important consumption for you today is relative to consumption tomorrow. If that rho is small, for instance, if it was 0, then consumption tomorrow matters to you just as much as consumption today matters. So, of course, if you just had a possibility to consume as much as you wanted, you may want to, and that's what this utility function tells you, you would want to maximize ever more in both periods. So that has to be a constraint. So you know, and in this example we assume this for certain, you know that in period 1 you earn income y1, and in period 2 you earn income y2. Now in period y1 you can decide to either spend or consume all of your income, or you can decide to actually save something in that period, okay? Or actually, under certain circumstances, you may save a negative amount, which means borrowing money. In period 2, your income is y2. Now, if you've saved something from period 1, then you also get your savings back with an interest rate. That interest rate is r. So you get back whatever you saved in period 1 times 1 plus r. So it has grown at a rate of r. That's the interest rate. And that means that in period 2, the amount you can consume is C2, but that has to be smaller or equal to that y2 plus S1 times 1 plus r. Now, perhaps I can already foreshadow that it turns out it will be equal to y2 plus S1 1 plus r. If you look at your utility function, you can see that we will not get an unconstrained optimum, because you will want to increase C1 and C2 as much as you can. So there won't be an unconstrained optimum. That means we will be landing on the constraint. So this is our constraint. Now, let me just highlight what our variables here are for our optimization problem. They are the consumption period 1 and 2. So they're here again, C1 and C2, and here. Okay. Now, what we assume we know on our sort of parameters are the y1 and the y2. They're assumed to be constant. And the two coefficients rho and r, which just assume we know them, and later we will get some values for this. Now, what I haven't highlighted yet is the S1, the saving in period 1, but as soon as we know C1, we will know S1, because S1 is just, and we just write that down, from here we know that S1 is just Y1 minus C1. So whatever's left over after consuming in period 1. So that actually means we can replace the S1 here in that constraint, so we get Y2 plus Y1 minus C1 times 1 plus R. Okay, so that's an alternative form for this constraint. And let us actually formulate now the constraint in the form which we needed in when we do a Lagrangian optimization, because we need a constraint function g of c1 and c2. We need that function, and we need that function to be larger or equal to 0. So that's pretty simple. We just bring the c2 to the other side, so we get y2 plus y1 minus c1 times 1 plus r, and then minus c2. Okay, and let us just formulate that in a slightly different way. We'll just factor out this term here, so we get y2 plus y1 times 1 plus r minus c1 times 1 plus r minus c2. Okay, so this is our constraint. So remember, our variables are c2 and c1, and you can see that this function is linear in c1 and c2. So we already know, that's important for later, that the g constraint is concave, as every linear function is concave as it is convex. So that means that potentially we will find later our Lagrangian conditions to be not only necessary but also sufficient conditions. So we're at a point where we can formulate our Lagrangian function. So let us do that. Lagrangian, which is a function of c1 and c2, and a Lagrangian multiplier lambda, is equal to the constraint function, the utility function. So c1 to the 0.5 plus 1 over 1 plus rho c2 to the 0.5 plus lambda, and now the constraint function, which is y2 plus y1 times 1 plus r minus c1 1 plus r minus c2. Okay, now I'll just draw a little orange line here so we know here's our constraint. Okay, so let's formulate the Lagrangian conditions as we know them. We need the partial derivative of that Lagrangian function with respect to c1, with respect to c1. That has to be 0. If we find the partial derivative of the Lagrangian with respect to c1, we get 0.5 times c1 to the negative 0.5, and then we have another c1 here, negative c1 1 plus r multiplied with the Lagrangian multiplier. The partial derivative of that is going to be negative lambda times 1 plus r, and that has to be equal to 0. Then the partial derivative with respect to the second variable, c2, ends up to be 0.5 divided by 1 plus rho c2 to the negative 0.5, and then we have a c2 here in the constraint, but that's just minus c2, so lambda minus c2, so the partial derivative of that is minus lambda equal to 0. And further, of course, we need our constraint c1 and c2 to be larger or equal to 0, and the complementary slackness condition that the constraint times the Lagrangian coefficient is equal to 0. So let's have a little shortcut here, because I already told you that if you look at the utility function, we can see that we won't find an unconstrained optimum. But let's sort of slightly formalize that by actually calculating the first order partial derivative. So if we set, well, let's just do it properly. So we set the lambda equal to 0. And then we get from the Lagrangian conditions, we get 0.5 C1 to the negative 0.5. Sorry, to the negative 0.5. That should equal to 0 because we are setting the lambda to 0. And then we get 0.5 1 plus rho C2 negative to the 0.5, and that is equal to 0. And we can see that will only be true if C1 and C2 is equal to 0. That means we wouldn't consume anything in either of the two periods. I should have said right from the beginning, that's of course not an economically sensible solution. So we will think about situations here where the consumption in both periods is larger than 0. Okay, and often that would be stated in the question. So that means from here there is no solution. Now, as you can see, these first two terms, these are actually the partial derivatives of the utility function with respect to C1 and C2. As we are already here, let's actually calculate the Hessian function of the utility function, because that will help us to decide whether the function itself, so the question we now want to ask is the utility function also concave? Because if both utility function and constraint are concave, then we know these conditions, the Lagrangian conditions, will not only be necessary but also sufficient. So let's actually find the second order derivatives. Okay, so the partial derivative of u, the second order derivative, that is meant to be a u, with respect to C1 twice. So we're taking this first order partial derivative, find the second order partial derivative, so we get negative 0.5 times negative 0.5, that's negative a quarter C1 to the negative 3/2. We are getting the second order partial derivative with respect to C2, so the partial derivative of this one with respect to C2 again, that is negative 1/4 1 plus rho. So it's negative 0.25, which is the same as negative a fourth times C2 to the negative 3/2. Now the cross partial derivatives will be 0, because you see the first one doesn't have a C2 and the second one doesn't have a C1. So the Hessian here will be negative a quarter C1 to the negative 3/2, 0, 0, and here we have negative 1/4 1 plus rho to the times C2 to the negative 3/2. That just fits. Okay, and what's important here to see is that the diagonals will always be negative. If the C1 and C2 are positive, then the diagonals will be negative. So we have, for the determinant, we have something negative times something negative, which is something positive, minus the product of the two off-diagonal elements, which are 0. So the determinant here will be positive, the elements will be negative. That means the Hessian is negative definite, and that means indeed that u, the utility function, is concave everywhere. And so what we've established, since the constraint is concave, the utility function is concave, we know that these Lagrangian conditions are not only necessary, but they are also sufficient. So that means if we indeed find a point which meets all of these conditions, then we know that that point will be or is the solution to our problem. Now, as it turns out, we didn't find such a point when we considered the case lambda equals to 0, i.e. when we looked at an unconstrained problem. That means what we really now need to do is we need to look at the constraint problem. So we're looking at the possibility of lambda being larger than 0. So for later, in the end, you're being asked for a solution to the problem when you're given certain parameter values. So let me give you these parameter values now. Okay, so parameter values, and that means you need values for all the pink values here. So that's y1, y2, as well as rho and r. And now let me give you these values. So let's assume y1 is equal to 100. So you know your income in period 1 is 100. You know your income in period 2 is 80. So perhaps you're thinking of reducing your work time, going to an 80% contract. Rho, that was the discount rate, which tells us how much we prefer consumption in period 1 relative to period 2, is 0.1. And R, the interest rate, is 0.05, so 5% interest rate. So what you could do here in this problem is you could plug in all of these values, 180, 0.1, 0.05, and then you could do now all of these calculations with these values rather than y1, y2, rho and r. And you will get the same result if you do all the algebra correctly. What I will do is I will just work with all the variables and the parameters, and only at the very end I will substitute in these values. And the reason being is that if we look at the parameters as they are, we can do some interesting economics. I can hint at some interesting economics you can do there. That's not so obvious if you immediately plug in the values. So what we do now with our we're looking on the constraint, we are setting lambda larger than 0. We're having here our constraint functions from the first. Let's just write it down. So from the first Lagrangian conditions we get 0.5 c1 to the negative 0.5 minus lambda times 1 plus r is equal to 0. The second condition gives us 0.5 over 1 plus rho times c2 to the negative 0.5 minus lambda is equal to 0. We're having two equations with three unknowns, c1, c2 and lambda. We need a third condition. We get that from the complementary slackness condition. If lambda is larger than 0, for the complementary slackness condition to be true, we know that the constraint g has to be equal to 0. So we go to our constraint equation, y2 plus y1 times 1 plus r minus c1 times 1 plus r minus c2 equals 0. So it means we are now having three equations with three unknowns. We are in business. We can potentially find a solution here. So what we're going to do, and that's often the easiest way, not always, we're going to solve the first two equations, which include lambda. We're going to solve each of them for lambda. So we're getting from the first one, we're getting lambda is 0.5 divided by 1 plus r times c1 to the negative 0.5, and from the second equation, we get lambda is equal to 0.5 divided by 1 plus rho, so that's Greek letter rho, times C2 to the negative 0.5. And if we now set these two equations equal to each other, or the two right-hand sides equal to each other, what we get is 0.5 divided by 1 plus r times C1 to the negative 0.5 is equal to 0.5 1 plus over 1 plus rho times C2 to the negative 0.5. And so what do we do with this? So what we're going to aim for is that perhaps what we do is that we find an equation for C1. So in the end, remember what we want is we want optimal values for C1 and C2. So let's solve this equation for C1, and then that will be the nucleus for our solution. So the best way perhaps to do that is we're having all sorts of negative powers in here, which are just a little bit annoying, but we can divide through by 0.5, and then the 0.5 disappears on both sides of the equation. And then perhaps what you can see here is that we have 1 plus r to the negative 1 times C1 to the negative 0.5. So, well, what we're going to do is we multiply through by a whole lot of stuff. First, we'll multiply both sides of the equation by 1 plus r. We also multiply by 1 plus rho. Then we get the 1 plus r and the 1 plus rho out of the denominator. Let's also multiply through by C1 to the 0.5 and by C2 to 0.5, because then we're losing the negative signs to the exponents. So what we get if we do this, we get C2 to the 0.5 times 1 plus r to the negative 1. No, I didn't actually. Let me do that here. So we multiply on the left hand side. We multiply with 1 plus r. The 1 plus r is lost. We multiply with 1 plus rho, so we get 1 plus rho. We multiply with C1 to the 0.5. That makes the C1 to the negative 0.5 disappear, and we multiply with C2 to the 0.5. And on the right hand side we are left with 1 plus r times C1 to the 0.5 with an argument just exactly similar. And now we have C2 to the 0.5, C1 to the 0.5. Let's actually square both sides of the equation, so we get the square roots eliminated, and then we have 1 plus rho squared C2 is equal to 1 plus r squared is equal to C1. And then we solve for C1, and what we get is 1 plus rho squared divided by 1 plus r squared times C2. So now we have C1 as a function of C2. By itself, that doesn't help us yet, because we want C1 as a function of all the things we know. That means y1, y2, r, and rho. But we have a second equation, that's our constraint equation here. And you can see from our constraint equation we can actually solve this very easily for C2. We just bring C2 onto the other side. So I actually do that right here, because that means we're just having this one here. So C2 is equal to Y2 plus Y1 1 plus R minus C1 1 plus R. Okay, so if we sub this into our, let's call this the hash equation. So let me continue here. So the hash equation with C2 substituted with what we know from the constraint, we get C1 is equal to 1 plus rho squared 1 plus r over 1 plus r squared times, and then we have y2 plus y1 1 plus r minus c1 1 plus r. Okay, so now we have the, let me just highlight this, we have a function with only one variable. This is exactly what we want, but that variable still appears on both sides of the equation, so we need to simplify this. So this algebra looks a bit more complicated and requires more steps, and needs to be if you plugged in all of the parameter values. Here, let me highlight them here. Remember, these were all the parameter values for which we actually have values. If you plugged all of them in, it will possibly require you a few less steps, but I want to see some interesting economics here. So we're going to bring that C1 over to the other side, so it's minus C1 times 1 plus r, but also times that 1 plus rho squared over 1 plus r squared. So if you bring that to the other side, because there's a minus, it will appear as a plus, so we get C1 plus 1 plus rho squared times 1 plus r over 1 plus r squared times C1, and that is equal to what's left on the right hand side, 1 plus rho squared over 1 plus r squared times y2 plus y1 times 1 plus r. So now all we're going to do is we're going to do a couple of simplifications. And you can see that on the right hand side we can cancel that 1 plus r and this one out. So on the right hand side we basically get C1, we can factor out the C1, so that's 1 plus rho squared divided by 1 plus r. And on the right hand side I do something which algebraically brings us no advantage, but gives us a term which has a nice economic meaning. We're going to take, you see there's a 1 plus r squared in the denominator here. We're going to bring one of these 1 plus r, so because that's 1 plus r times 1 plus r, we're going to bring one of those into the parenthesis here. So what we are left with then is 1 plus rho squared divided by 1 plus r, so only one of them, not the squared, and in the parenthesis we're having, because that's in the denominator, we're having 1 plus r to the negative 1 times y2 plus y1 times 1 plus r times 1 plus r to the negative 1, so the 1 plus r and the 1 plus r to the negative 1 cancel each other out, and that's just y1. And this is what I wanted to get to, because this term, especially those of you who do any finance, and especially financial decision making, this here is just the net present value of your income stream. You're having income today of y1, next period your income is y2, but that's discounted by the discount rate by 1 plus r. So I'll give that a name here, net present value of y, NPV y. Right, so those of you who've seen that, you will hopefully recognize that. Those of you who don't do finance have perhaps not seen that. For you, this is just a short version of writing this parenthesis term, so I don't have to write so many things. Okay, so once we have this, I'll make on the right hand side, I'll make a we'll continue here. Okay, we have a line here. We continue here. I'll do one further algebraic simplification on the left hand side. Instead of 1 plus rho squared over 1 plus r, I'm expanding that first term, and then we are getting 1 plus r plus 1 plus rho squared divided by 1 plus r, and that is 1 plus rho squared. That rho looks like a p, but it's a Greek rho. 1 plus r times npvy, that present value of y. That's that green term here. And now I'm just bringing that parenthesis term on the left hand side over to the right hand side, because then I've isolated the c1 on the left hand side. So we're getting c1 is equal to 1 plus r over 1 plus r plus 1 plus rho squared times 1 plus rho squared 1 plus r times the net present value of the income. And again, let me use a nice red pen to see where things simplify here. See, 1 plus r and 1 plus r here cancels out, such that on this side we are left with 1 plus rho squared divided by 1 plus r plus 1 plus rho squared times the net present value of the income. So that is our optimal C1. If we now, let me actually put an asterisk here to indicate that that is the optimal C1. We'll continue over here. Now we want the optimal C2. Once we know the C1, the optimal C1, we can get the optimal C2. You can see here from the hash equation, we can turn the hash equation. So from the hash equation, we can solve that for C2. We know that C2, the optimal C2, if we use the optimal C1, is 1 plus r squared over 1 plus rho squared. So if we substitute our optimal C1 in, we're getting 1 plus r squared over 1 plus rho squared, and now times the optimal C1, which is 1 plus rho squared divided by 1 plus r plus 1 plus rho squared times the net present value of the income. And again, let me get the red pen to indicate where things nicely simplify here. You can see we're having 1 plus rho squared here and 1 plus rho squared here. That is just beautiful, because what we get is 1 plus r squared in the numerator divided by 1 plus r plus 1 plus rho squared times the net present value of the income. Okay, so now we're having two equations for C1, the optimal C1, and another one for the optimal C2. This is perhaps a nice time to actually plug in our parameter values into these equations. So if we do that for C1, let me do that here. Down here for C1, we're getting 1 plus rho. Rho is 0.1, so we're getting 1.1 squared divided by 1 plus r is 0.05, so that's 1.05 plus, and then again 1.1 squared, and that is equal to the net present value of the income that is here. Okay, so that is, actually let us just calculate what the net present value of the income is first, and then we don't have to do that twice. NPVY is, given our value, so I do that here on the left, is 100 is Y1, 100 plus Y2, which is 80 times 1 plus R, 1.05 to the negative 1. When you calculate that, what you get here is 176.1905. Okay, so it's a little bit less than the sum of our two incomes, because this income in the second year is discounted by a certain amount. Today it's worth less than the actually 80 you will get tomorrow. So that's our net present value of income, 176.1905. So with that we can go back to our equation for the optimal consumption in period 1. We have our factor times 176.1905, and what we get is, let me just make sure I get that right. Yeah, that's 94.3321. And then we can also, of course, calculate the optimal income in period 2. So I'll just follow up on that here. 1 plus r squared is 1.05 squared divided by 1.05 plus 1.1 squared times, and we do that in green again to be consistent, the net present value of your incomes, and the result of that is 85.9513. So let's contrast this. If you look at that with your income. So in period 1 you get an income of 100. The amount you consume in period 1 is only 94.3321. So you learn from here that you're actually saving a certain amount in period 1, and the amount you save is 5.6679. Okay, you're almost saving £6 if these were pounds. And then in the second period you're consuming 85.95. Now your income in the second period is only 80, but you're consuming 85. How does that work? Well, you've saved an amount in period 1, and you get that back in period 2 plus interest. So that 85.9513, that is the income you earn in period 2 plus the saving 5.6679 times 1 plus the interest rate, and that is 1 plus the interest rate is of course times 1.05. Okay, so that's what you can consume in period 2. You can consume more in period 2 than you earn because you saved something in period 1. And for this particular constellation, this particular utility function we used here, and these particular parameter values, the best thing you can do for your utility is to consume in period 1 94.33, save almost £5.70, and then in period 2 you can use that saving, including the return, to consume on top of what you get as your income in period 2. So why can we stop this problem here? This is the optimal solution. Okay, the one which we just discussed is the optimal solution. And why can we do that? Well, because as we established at the beginning, our Lagrangian conditions are necessary and sufficient. That means if we find a point, as we have, and I'll confirm it just in a moment that it is, if we find a point which meets all of the Lagrangian conditions, well, then we know that is the solution to the problem. And we knew the Lagrangian conditions were necessary and sufficient because both the constraint was concave, G was concave, and we established that the utility function, the function which we are maximizing itself, was also concave. That was enough to say that the Lagrangian conditions were necessary and sufficient. And the very last, sort of the icing on top, is what happened to our Lagrangian multiplier, because if you have one constraint like this, we need this Lagrangian multiplier to be positive. So let us just go to let me highlight an equation for the Lagrangian multiplier. Here we have it. Okay, we found out in our algebra that lambda is equal to 0.5 divided by 1 plus r times c1 to the negative 0.5. So we could plug in our C1, which is 94, approximately in here, and you can see what we get in our R value, which is 0.05. And what you will get is the C1 is positive to the power of negative 0.5. That will still be positive, okay, because it basically means it's 1 divided by the square root of 94. That's still positive. Then multiplied with 0.5 over 1 plus r, and r is also positive. Everything's positive here. The lambda is positive. Okay, so we know that lambda is larger than 0. That's all we need to know. And that's what we need the lambda to be. We need it to be positive. So we've worked through this problem with quite a bit of algebra. The algebra was a bit more cumbersome, messy, because I refused to use the parameter values right from the start. If you had done so, possibly the algebra would have come a little bit easier. But I wanted to do this because I wanted you to understand the role of the net present value of the income here. Okay, because I hope that all of you who are doing any finance courses will recognize this and see here the solution to a typical two-period utility optimization problem. That's the end.